Today we're going to look at limiting and excess reagents. We've started this lesson, but we're going to complete it today and we're going to work through a number of problems. When we're looking at limiting and excess reagents, it means that one part of the reaction is being controlled by the limited amount of molecular compounds that we have. In this particular example, we need to make cheeseburgers for our customers, and they specifically want 2 burgers and 1 cheese slice. Our supplier has given us 10 burger patties and 50 cheese slices. This means then that we can only build 5 cheeseburgers because we only have a limited supply of burger patties. And what you'll see is that we'll have a leftover of 45 cheese slices. So our limiting reagent in this particular example is the number of patties, and our excess reagent is the number of cheese slices. Again, we've been asked by our customer to build bicycles that have 2 wheels and 1 handlebar. Our supplier has given us 6 wheels and 9 handlebars, and we can look at the wheels and the handlebars as our reactants, and we can look at the bicycle as our product. And so our 6 wheels is going to control how many bicycles that we build. It's going to control the amount of product that we have. And in this particular case, we're going to have 3 bicycles that we can build. We're going to consume all of our reactant, we're going to consume all of our wheels, and we're going to be left with 6 handlebars, which will be our excess reagent. So this again is looking at that of the 2 reactants, 1 will not be completely used up, and that the one that is not completely used up is a limiting reagent. And so the one that is completely consumed is going to be the one that controls how much product is made. So same 5 steps that we look at with a little bit of a twist. We always start out with a balanced equation for the reaction, and then we need to look at the reactants that are involved. We need to write down the given information that we've been provided. Then we need to calculate the number of moles for each reactant. This is a very important step. Then we need to look at the relationship between the 2 reactants, the mole ratio that is there. From there, once we determine which is the limiting reagent, we can go forward with the rest of the steps that we follow in standard stoichiometry. We can take the moles of the limiting reagent and we can use those as our given moles, and then we look at the moles of our wanted, and then from there we go forward to calculate out the component that we're looking for. So in our first example, we have 5 grams of sodium hydroxide added to 50 mils of 1.25 molar nitric acid. And it's asking us to calculate the mass of water that forms. This is one way that we can decode that this is a limiting reagent question. So let's start this off. And in this particular case, I'm going to write water as HOH because over here we have a hydroxide, and this tends to be a way that is easier for people to look at hydroxides rather than trying to balance hydrogens and oxygens. So as we can see, this ends up being balanced: 1 sodium, 1 sodium, 1 hydroxide, 1 hydroxide, 1 hydrogen, 1 hydrogen, 1 nitrate, and 1 nitrate. So we start off by writing off our givens. And then the next step that's very important is that we have to calculate the moles of both reactants. So we're going to look at sodium hydroxide first. And we're going to divide this by the molar mass. And so we end up with 0.125 moles of NaOH. Always get in the habit of writing the reactant for the moles that you've just calculated. This will help keep your numbers straight when we get into more complex steps. So looking at nitric acid, okay, so we've calculated out the moles for both of the reactants. The next thing that we need to look at is the relationship between the reactants. And so arbitrarily, I just work from left to right. So there's 1 mole of sodium hydroxide in the reaction, and there's 1 mole of nitric acid. And this is going to be equivalent to 0.125 moles that we calculated over 0.0625 moles that we also calculated. Now to look at the mole relationship, you're going to cross multiply with the number of moles. This is step number 3, looking at the mole relationship between the reactants. So what we see here is that 0.0625 times 1 is going to be 0.0625, and that is less than the 0.125 moles for sodium hydroxide, which means that nitric acid is our limiting reagent. Okay? So once we know which one is our limiting reagent, we can use those moles to continue on with regular stoichiometry. So we're going to take 0.0625 moles of the nitric acid. We're going to multiply it by our mole relationship for our reaction. So when we're looking at water, we see that there's 1 mole there. So we have 1 mole. And we have 1 mole here of water to give us 0.0625 moles of water. And then from there we can calculate out our, again, this is our given and this is our want. So you can see that we're at step 3/4 in our regular stoichiometry. And we're going to take our 0.0625 moles of water, and in order to calculate out the mass, we're going to multiply out by the molar mass. And looking at significant digits, when we go up here, we have 5 and 50 and 1.25. Those all have 3 significant digits. So our answer is going to be 1.13 grams of water. So same 5 steps, just to recap. We have a balanced reaction right here. We've figured out the moles of the reactants. We figured out the mole relationship between the reactants, and then we figured out the mole relationship between what we have given and what we want. And then once we have the moles of our want, we can figure out our final value. So same 5-step process that we've typically gone through. Next example. If 20 mils of 3 molar sulfuric acid is added to 15 mils of 5 molar potassium hydroxide, what mass of water can form? Okay, so the first thing that we need to look at is we need to look at a balanced equation. And you're going to make sure that you're putting in your states. I'm just being cheap because I don't have a lot of room on my writing tablet. And again, I'm writing water as HOH because we have a hydroxide right here. We have 2 potassiums here, so we need to write a 2 for the 2 Ks here. That then means we have 2 hydroxides. We have to write a 2 here, 2 hydrogens, and 2 hydrogens. Now we're balanced. We're going to write down our given information. And 15 mils. Whoops. Okay, so the next major step is to find the number of moles for each reactant. And again, making sure that you're writing down what those moles belong to for future reference. Okay, so the next step, the third step, which is the mole relationship between the reactants, we're going to look at 1 mole of sulfuric acid to 2 moles of KOH from our equation here. And then we're going to compare that to the calculated amount of moles that we have, 0.06 versus 0.075. Now, the number of moles is going to be limited. So we look at cross multiplication, which means that 0.075 is going to be less than 0.12, which then tells us that KOH is our limiting reagent. Because this is our limiting reagent, it's going to be the number of moles that we use to figure out the rest of our question stoichiometrically. So, starting off, now we're going to look at the mole relationship with the entire reaction. So, this is the moles of our limiting reagent. We're going to look at the moles of our given. We have 2 moles of KOH from our reaction equation, and we have 2 moles of water. So, this is the exact same step that we have in regular stoichiometry. So we end up with 0.075 moles of water. This is our given, and this is our want. Okay, now we're going to calculate out the mass of the water that can form. So we're going to take our number of moles of water that we have, and we're going to multiply it by our molar mass of water. When we look up at our question up here, we see that we have 2 decimals, two significant digits, 2 significant digits, and 3. So our limiting is going to be 2 significant digits, which is going to be 1.4 grams of water. Oh, and I missed the question. Looks like it. Okay, well, question number 1 is 350 grams of KOH is added to 1 liter of 6 molar phosphoric acid. Which reagent is in excess, and how many moles of the excess reagent are there? Okay, so the first step that we're going to need to do is we're going to need to write out the balanced reaction. So we're going to look at KOH reacting with phosphoric acid. And again, you're going to write in your states. And again, I'm writing water like this. There's nothing saying you can't write it as H2O. We have 3 potassiums here, so we need to put a 3 there, which means we have 3 hydroxides. Put a 3 there for 3 hydroxides. We now have 3 hydrogens, and we have 3 hydrogens. Our phosphates balance out. Writing out our given information, we have 350 grams of potassium hydroxide, and we have 1 liter of 6 molar phosphoric acid. So first things first, we need to calculate out the number of moles for each reactant. So we have 350 grams of KOH. We're going to divide that by the molar mass. And you're going to make sure that you identify where those moles came from. And figuring out the number of moles for phosphoric acid. Okay, now we need to look at the relationship between the reactant, the moles. So we have 3 moles of potassium hydroxide to 1 mole of phosphoric acid coming from our equation. Then we look at the number of moles. We had 6.2377 versus 6.0 moles. When we look at how the reactants are going to be consumed, we see that 6.2377 is less than 18.0 moles of phosphoric acid. Therefore, KOH is limiting. The question asks us which reagent is in excess. So phosphoric acid is in excess. And it has a value of 6.0 moles. That's how you would answer this question.